show up naturally once we ask some basic questions about gradient flow that we saw in the previous lecture. So we will talk about them, how to establish them, what they're good for, and then in the next lecture, we will see how functional inequalities are actually interesting in their own right in probability in high dimension. But in this talk, we will still focus on the setting of gradient flows on the Wasserstein space. So again, just for reference, this is the book of Villani, the first one, Topics in Optimal Transportation. Chapter 9 is a pretty good reference for what we'll cover today. And I just want to recall some basic stuff from the previous lecture that Sinho gave, and I will keep it here because we will use these things over and over. So first, let me remind you that if we have a functional f on the Wasserstein space, then the way we define its derivative is by looking at curves which satisfy this equation, this continuity equation. So we have partial t of mu t plus the divergence of mu t times vt equals 0. So we look at such curves, and then we differentiate the functional along the curve, and we value the derivative at 0, and then what we should get is the gradient of the functional at mu 0 inner product with v0, which is the value of the vector field vt at time 0, and then we take this inner product with respect to mu 0. So this is a vector field, and this is going to be a vector field, so everything is a function of x, and then we integrate against mu 0. So that's the natural definition that you have in Euclidean space, and we use the same definition on the Wasserstein space. For the Hessian, we had to work, instead of working with general curves, we work with geodesic. So now mu t is going to be some geodesic going between mu 0 and mu 1. So we have this t, which is the optimal transport map between mu 0 and mu 1. So mu t, which is defined as 1 minus t times the identity map plus t of x, and then you push forward mu 0. That's just a geodesic between mu 0 and mu 1. So then you take such curve and you look at the second derivative of your functional and you evaluate at 0, and then you get the Hessian of your functional, and what applied to the tangent vectors of the curve at time 0, and the tangent vectors to the curve at time 0 are just tx minus x because we're using geodesics. And the main example that Sinho focused on in the previous lecture, and also the one we'll focus on in this lecture, is this, okay, this is terrible notation, is the scale divergence. So f of mu was equal to the KL divergence between mu and some probability measure E minus V. And I remind you that he computed the gradients of this functional, that we found that the gradient was equal to nabla V plus gradient log mu, so we can assume that mu has density. And he also computed the Hessian evaluated at these tangent vectors, and we found out that, so the tangent vector is tx minus x, and we found out that the Hessian was just equal to the gradient of the transport map minus the identity, and then you take the Hilbert-Schmidt norm, plus, and this term is important, we have the Hessian of V, and then applied to the tangent vectors. And then he also spoke about gradient flows. So gradient flows were just taking the continuity equation, such as here, but taking the vector field to be the gradient of the functional. And then there's a simple computation of just what happened when we differentiate the functional along the gradient flow. So we found that the derivative is just equal to the gradient squared, minus the gradient squared. And this is the same computation that you would do in Euclidean space. So this is a quick recap of what happened in the last lecture. So any questions before, because if things are unclear now, it would only get worse. Okay. Good. So let me start right away with the first theorem that we'll prove. We'll see how much we cover. But most of the results will be similar to this one. This is perhaps the best one to kind of, at least to present. And the basic question is, that we want to understand is, suppose we take a gradient flow of this KL functional. We expected eventually the law of mu t to just to converge to the stationary distribution E minus V. I'll take it as a given for now, but remember that this gradient flow is just the Fokker-Planck equation, and we know the Fokker-Planck equation converges as time goes to infinity to the stationary distribution. So we expect that mu t will converge to E minus V, and we want to know what is the speed of this convergence and in what sense does it converge. So that's what the next theorem is going to tell us. Of course, if you don't make any assumption about V, you cannot expect anything like that. So we'll make some assumption, then we'll see how to use the tool that we saw in the previous lecture. How can we use them to prove a convergent result? So let's take our functional to be the KL divergence. And let's take mu t to be the gradient flow of the KL divergence. So we'll write gradient flow of F. So here is the assumption that we used this assumption last time. So if the Hessian of V, where V is the potential of the stationary distribution, if it is lower bounded by alpha, so here alpha is some non-negative number, here we mean alpha times identity, then we have exponential convergence in the sense of the KL divergence. So if we look at the KL between mu t and E minus V, and remember that when this term is 0, mu t is equal to E minus V. So this is not a distance between the two probability measures, but it is a way of measuring how far you are from being the stationary distribution, because it would be 0 if and only if mu t is equal to E minus V. And this is upper bounded by e to the minus 2 alpha t, and then times how far you were when you started. So I should say there's some good chance that at some point I will mix between 2 alpha and 1 over 2 alpha, things like that. You can always figure out which one it should be. The point is, as alpha gets bigger, things become more convex. You expect to have faster convergence. So this way you can always figure out what's the right way of doing it. Okay, so this is roughly speaking how far we were from the initial, from the stationary distribution when we start, and then the statement is that we have exponential convergence in T. Okay. So let's prove that there. The idea of proving the theorem is establish differential inequality for the KL divergence between mu t and E minus V. So if you're not familiar with differential inequalities, so I'll just remind you, I mean, this is a type of differential inequality that we will use. Of course, there are many more. But so just imagine that you have a function g on Rn, and you know that its derivative is upper bounded by minus lambda times the function itself. So differential inequality, so if we had equality, this would just be some ODE. We don't have equality, we have inequality. But for our purposes, this is just as good, because once you have a differential inequality like that, you can conclude that g of t is upper bounded by E minus t lambda g of 0. The point being that we know how to solve this equation. The solution, if this was an actual identity, if this was an ODE, this would be solved by this function here. So because we have an inequality, you can upper bound the solution. You can upper bound GT by the solution to the corresponding identity. Okay, so I'll use this basic idea over and over. So we want to do the same thing, but for this functional here. So in order to do that, we need to differentiate in time the KL of ut with respect to E minus V. So let's try to do that. And ideally, once we differentiate this in time, we'll get some expression which depends on KL, and then we will get our differential inequality. But let's see if we can actually get that. So let's do the computation. So remember, because mu t is just a gradient flow of f, I'm just using this fact here that when we differentiate the functional along the gradient flow, we just get minus the gradient squared. Okay, but now you also remember that we actually know what this gradient is equal to because it's the gradient of v plus gradient log mu. So we can write it out explicitly. Okay, maybe I'll do it in 2 steps. And then you can just rearrange. You get the gradient of log of mu t over e minus v. And maybe this expression is familiar. So what is this expression? Anyone know? So it's probably obvious, so that's why no one wants to say that. That's okay. So, okay, yeah, I will just give it a name. But this is the relative Fisher information of mu with respect to e minus v. And this is essentially what's called the de Bruijn identity, which is what happens when you take a solution to the heat equation and you differentiate the entropy along the heat equation, you get Fisher information. So this is analogous. We're just looking at KL instead of entropy. Okay, so good. We differentiated the KL. We were hoping that we would get something here which depends on KL, and then we would have a differential inequality, and then we will be able to get a conclusion like that. Unfortunately, this is what we have, which doesn't look anything like KL. So the way this field works, and also related to the Bakri-Emery calculus, so like I said in one of the lectures, integration by parts can take you very far. So that's one thing you can always do, which is easy because integration by parts is identity. There's another easy thing that you can always do, which is differentiate again, which is exactly what we're going to do. You don't differentiate 3 times. That's just too much. You don't do that unless you want to be very fancy. So we'll take another derivative. I'll just say there is another thing that you can do is to do Cauchy-Schwarz. That one is harder because inequalities are actually difficult. Identities, it's algebra. You just give it to a computer. Cauchy-Schwarz is a little more complicated because you need to know, what to apply Cauchy-Schwarz on. But we're not going to do a lot of Cauchy-Schwarz, maybe just once or twice. So mostly it's just going to be identities or really pretty simple inequalities. Okay, good. So because we're stuck here, we didn't get KL. So when you don't know what to do, you just differentiate again and you see what happens. So let's do that. Okay, so just by definition, this is the second derivative of KL. We know what the derivative of KL is. So, okay, so just equal to partial t and okay, so now we need to know how to differentiate that. And now what we will do is we will just use the same computation that we would have done in Euclidean space. So what would be the analog of that in Euclidean space? So maybe let's do hopefully it will fit in this small box. So imagine we had a gradient flow. So we're looking at the particle perspective. So xt is just a point in our n, and the analog of that would be here mu t. So let's do the same computation in our n. So what is it we're trying to understand? We're trying to understand what happens when we differentiate the norm squared of the gradient, right? That's the type of expression that we have here, where the function f here is played by the KL here. So in order to do that, you just do the chain rule. So you get a factor of 2, and you do the chain rule, so you get the Hessian of f of xt. Then you apply it to xt dot, and then you have another term here, which is gradient of f xt. But we assume that xt dot was a gradient flow, so we just plug it in, and we get -2 the Hessian of f of xt, gradient of f of xt, and then multiply by the gradient of f of xt again. So that's it, would be the Euclidean computation. So we're just going to use that computation here because we saw the calculus works in a similar way. So if I apply it here, we get 2 times the Hessian of KL of mu t with respect to the stationary distribution, and then we just multiply by the gradient twice. Okay, so this is now a pretty good computation. Why? Because we can actually understand this Hessian and we can bound it. Because, if you remember, we had an expression for this Hessian in the case of KL. One term was always non-negative, this term here. The other term had the Hessian of V, the V being the potential coming from the stationary distribution, multiplied to Tx minus x, then Tx minus x. But we made this convexity assumption here, so we can apply it here, and then we see that the Hessian of V is alpha convex. So we can lower bound it. This is by equation 2, by 2 alpha times the gradient of the KL divergence. Okay, so, remember, what is it we want to do? We wanted a differential inequality for KL. We wanted to differentiate this and get something here which depends on KL. That did not happen. So we differentiate again, and then we got this expression. So where do we go from here? This seems like things are only getting more complicated rather than easier. But actually, if you think about it for a second, this inequality is basically a differential inequality. It's just a differential inequality for the derivative of KL rather than KL. Because here I have partial t of KL, and here we have this gradient, which is of course just partial t of KL. So actually we did manage to get a differential inequality here, but rather than get differential inequality for KL, we got a differential inequality for partial t of KL. But that's basically just as good, because if we have a differential inequality for partial t KL, we just integrate out that differential inequality and we get what we want. That's basically the idea. So I will now show you how to do it. Any questions on? This lecture is going to be kind of computationally heavy, a little bit like that. So, okay, good. So this idea here, we're doing it all in the Wasserstein space setting with this autocalculus business and all that. But I just want to say that really we don't have the time, unfortunately, to talk about it. But if you're interested in the Bakri and Marie semi-group theory and how it works, the computation there are very similar to this type of computation. They're done in a different language. We don't have this interpretation of the Wasserstein space and all that. But this type of differential inequality, differentiating twice in order to use convexity, this is the heart of the Bakri-Marie theory, which is actually, it's very non-trivial. This idea, like, how do you take an assumption like that and actually get something from it? The idea that once you differentiate it twice, you will get differential inequality because of this assumption is non-trivial and is really at the heart of the theory. Also, this type of computation has its analog in the Bakri-Marie theory, and it's kind of if you ever try to attempt it, it's pretty tedious, and you need to know what you're doing, and you need to believe that something will come out of it. Otherwise, it's kind of difficult to do it and knowing that it could be a mess. So that's really the heart of the business here. Good. So at this point, we have this inequality. But remember, what we really wanted was differential inequality for partial t. But that's okay. We're basically there. So here's what we do. So we define this function phi of t to be the gradient of KL minus 2 alpha of mu t. And the reason why we define this function is because if you stare at it for a second, you will see that this is getting pretty close to the type of inequality that we want. But let me do that. So let's just differentiate this function. And so the first derivative, it's partial t of this norm. But we did this computation over here, so I can just use this estimate here in order to bound the first derivative of this term. So if we do that, then we have an upper bound, if that's how the sign works, of the gradient of KL. And then we differentiate in t this expression, but we know that the derivative of KL is just its gradient, so we get plus 2 alpha, and then again we get the gradient of KL. But this is, of course, just equal to 0. The two terms cancel. So we see that phi prime is decreasing, and therefore we can now compare the value of phi at different points. And this type of idea will repeat itself over and over. So in particular, so phi is decreasing, and because we already assume that it requires a proof, but we assume that mu t converges to e minus v as t goes to infinity. If we look at the limit of phi t and we just stare at it, it's just equal to KL of e minus v with respect to itself. But then this, well, the whole thing is just 0, basically. Yeah. Okay. So anyway, the point is to now compare 0 and phi of 0. So let's see. So the idea is that phi was decreasing. It decreases eventually to 0. So it must be the case that at time 0 it's greater than 0. Okay, now we just plug in t equals 0. And what we find is, so mu t just started at some measure, mu. So we just plug it in. Okay, I'll just write it equivalently. So if we just plug in 0 into the definition of phi t, we just find that for every mu, the gradient of KL is lower bounded by 2 alpha times KL. So here what I used, we're evaluating the thing at time 0, so mu of 0 can be whatever mu I want, so I just plugged it in. So now this really, you do get the differential inequality, because now what you can do is, you just plug in this inequality into here, and you get exactly the type of differential inequality that would lead to exponential convergence. Yes?
To argue that the limit at was use the fact that it's decreasing, that the derivative is always.
Yeah, I guess you also have to argue about this term. Yeah. Yeah. Okay, so is it clear? I mean, I can write out explicitly how Yeah.
Compared to the usual derivation for like from modified log-Sobolev inequality to something, somewhere hidden inside here is a modified log-Sobolev inequality for the derivative.
So, right. So this inequality that we proved here, maybe, okay, I was going to write it in a minute. This inequality is just log-Sobolev inequality. Okay, good. Okay, I was just going to get to that. Okay, I just want to make sure that this proof is clear. Okay. Yeah, so just to emphasize again, remember, because I'm kind of skipping the step, so just remember the idea was that if we can bound the time derivative of KL by KL, then we would get the differential inequality that we want. But this is a time derivative of KL, and now we have an inequality which describes it in terms of KL, so that's exactly what we wanted. Okay, so good. So let's talk about the log-Sobolev inequality. So if we look at the proof of the theorem, so we prove this exponential convergence, but on the way to proving this exponential convergence, we prove the inequality here. So let's just write it out explicitly. Also remember that this gradient had this Fisher information expression. So let me call this inequality star. And also remind you that this is equal to, sorry if you cannot see, this is equal to the, so I'll say it in a word, this is equal to the relative Fisher information between mu and the stationary distribution. So we can actually, we'll just turn it into a definition. So log-Sobolev inequality, so here's the definition. So we'll say that e to the minus v, we assume that it's a probability measure here. Satisfies LSI, so LSI is log-Sobolev inequality with constant lambda if star holds for all mu, and by that we just mean that the KL between mu and E minus V is upper bounded by lambda times the Fisher information, relative Fisher information between mu and E minus V. So maybe just as a sanity check, just so that we're all on the same page. So what's an example of a measure that satisfies that? What assumption do we need to make on the measure in order to get it? I claim that we basically did that. So if you paid attention, you know the answer to it. Exactly. So basically what we've shown in the process of proving the theorem is that if the Hessian of V is lower bounded by alpha, then this inequality star was satisfied. Yeah. If you didn't get it, don't blame yourself. You can blame me for not explaining it properly. So the example is indeed that the Hessian of V is alpha convex or alpha strongly convex. Then E minus V satisfies LSI with constant 1 over 2 alpha. So here we kind of motivate the log-Sobolev inequality just because that's what comes up naturally in trying to prove this exponential convergence. But actually the log-Sobolev inequality can be motivated from many different directions and it shows up in many different contexts. So in information theory, it's a very fundamental result because you can view it as a statement that relates entropy and Fisher information, which is of course something coming from information theory. In mathematical physics, this inequality was used in quantum field theories. And as we will see in the next lecture, it can be used in probability in high dimensions. Okay. Questions? Good. So in the next result, what I want to show you how, if you know this particular log-Sobolev inequality, you can actually deduce a different inequality for it. It's going to be called Talagrand inequality. And that inequality is also important in probability in high dimensions, and we will see it hopefully in the next lecture how to use it. I should also say that this next theorem, in some sense, I think was the first result that was proved using this type of calculus for which, at the time, there was no other proof. People conjectured that this thing is true, but there was no other proof. And all this machinery helped to lead to a proof. So let me write out the statement. So we'll call it LSI implies Talagrand inequality. So suppose e to the minus v satisfies LSI with constant lambda, then it satisfies Talagrand inequality with constant 4 lambda. And what is this inequality? It relates the Wasserstein distance between mu and E minus V to the KL divergence. This is for all mu. So let's stare at this inequality for a second and see that it's highly non-trivial. The Wasserstein distance, that's one way of measuring how close are two probability measures to each other. We have measure mu and we have E minus V, and we want to know how close they are to each other. The KL divergence is another notion which tells us how two probability measures, how close they are to each other, because, for example, if mu is equal to E minus V, this would be 0, and that's the only way in which this is 0. In general, if you have two metrics, it's not necessarily metric, you have two quantities which capture how close our two probability measures are to each other, there is absolutely no relation between them. And when there is, it's actually very useful. Things like Prinsker's inequality that relates total variation to other things become very, very useful. So a priori, you wouldn't expect to have any connection between these two notions of distances. But what this theorem is telling you is that if the measure E minus V satisfies log-Sobolev, then actually you can relate the W2 distance between mu and this E minus V to the KL between mu and E minus V for every measure mu. So as a particular example, when this is true, again, we go back to the case where the Hessian of V is lower bounded by alpha. So maybe if I didn't make it clear, the Gaussian is a great example of that, of such measure, because the Gaussian is just e to the minus x squared over some variance. So for such measures, we can actually always compare the Wasserstein distance to the measure with a KL to the measure. Okay? So the way we're going to prove this theorem is also going to be following similar type of calculus, but we'll need some different ideas. Okay.
Discrete setting and analog would be Prinsker's inequality.
Yes.
And that is sort of equivalent to Hoping lemma and therefore the
yes.
log-Sobolev for the hyperspectrum. Is that similarity?
So what we will see in the next lecture is that both log-Sobolev inequality and Talagrand inequality are related to concentration of measure. In particular, if a probability measure satisfies one of these inequalities, roughly speaking, it will have sub-Gaussian tails. But the story is actually much more nuanced, so we'll have to wait for the next lecture to see how it goes. But both of these inequalities are related to this type of properties. So in that sense, yeah. Okay, so maybe, yeah, I guess I can write as a corollary. I can view it as a corollary or a simple exercise. Very simple. So in particular, if we look at the gradient flow, it will also converge in Wasserstein distance if we assume that E minus V satisfies the log-Sobolev inequality. Okay, so let me just write it like this. So we have convergence not only in KL, but also in W2, but convergence in KL would be stronger than W2 under these assumptions. So let's see how to prove it there. So as usual, we differentiate. So let's try to differentiate the W2 distance between mu0 and mu-t, where mu-t again satisfies the gradient flow. So let's just write out first the definition of derivative. So here we're going to have mu-t plus epsilon, and here we'll subtract mu0 mu-t over epsilon. And now what we will do is we will use the triangle inequality on the first term, the fact that W2 satisfies the triangle inequality. So this is upper bounded by this limit where we replace this first term here by first going from mu0 to mu-t, and then going from mu-t to mu-t plus epsilon. So here we've just replaced the first term, and then we'll subtract this last term, but now we see that there is a cancellation. So we get the limit as epsilon goes to 0 of the distance between mu-t and ut plus epsilon over epsilon. And now we will use the Riemannian perspective, and we'll say that this is equal to the partial t of mu-t. Because the idea is that we start at mu-t and then we perturb it a little bit, going to mu-t plus epsilon, and we look at the distance. So again, if you want to convince yourself that something like that makes sense, just pretend that this is Euclidean distance and do the analogous computation. Okay, but we said that we know that mu-t is a gradient flow. Yes? The gradient flow of the KL. Yeah. So. And now we will use this inequality. So maybe I'll write here, it just, this is a Riemannian computation. And here we will use the fact that mu-t, I'll just write gradient flow. So we have the gradient of mu-t with respect to E minus V. Okay, let's continue here. Recall that we've already computed this term, and it was the Fisher information. In fact, the square root of the relative Fisher information. But now it's exactly the point where we can use the assumption that E minus V satisfies the log-Sobolev inequality. Because the assumption that it satisfies the log-Sobolev inequality meant that this Fisher information formed an upper bound on KL divergence. So we will use it here. So what this implies is that if we look at partial t of W2 mu 0 mu t, it's upper bounded by the square root. And now, using LSI, we get square root of lambda, and here we get I ut minus v over the square root of the KL divergence. So this is just a simple rearrangement of the log-Sobolev inequality. Okay, and now we will do something similar to what we did before. We will define phi of t to be square root of lambda, square root of KL ut, E minus V, plus W2 mu 0 mu t. So just to maybe save on some computation, I'll just show the main step, and you can use it as exercise. So then you differentiate phi of t, and you show that it's smaller than 0 because of the inequality here. And once you show that it's smaller than 0, the derivative, you conclude that phi of 0 is greater than phi infinity. You compute phi of 0, you compute phi infinity, and you'll get exactly Talagrand's inequality. Questions? Okay. So the results so far were about settings where we assume some strict convexity, because we said that the measure satisfies log-Sobolev inequality, and so far the only criterion that we saw for this to happen was if we have strong convexity, in the sense that this Hessian of V was lower bounded by alpha, where alpha was some positive number. So what I want to show you next, I'll just sketch it, and maybe we'll finish a little early today. I just want to sketch how to get some results when we just have convexity without strict convexity, or even when we don't have convexity at all. We just have semi-convexity. So we don't expect to get exponential convergence, but hopefully we'll get something. So that's what I want to show you. So I'll write two theorems, and then I'll sketch the proof for both of them. So in the first theorem, we will compare, this is H is the entropy. So it's not the relative entropy, it's just H of, so H of mu is equal to mu log mu. And we will compare the entropy of mu t to the entropy of the stationary distribution, mu t still being the gradient flow of KL. And we will upper bound it by the W2 distance between the initial point. And then we need some function of t, but you see, we don't get anything exponential here. We're only getting algebraic convergence. Okay. Here's another result. So let's suppose that the Hessian of V is lower bounded by some constant C, but now, to emphasize, C is going to be any number. It doesn't have to be a non-negative number. It can be any number. Okay. So then, we get what's called HWI inequality. So we can upper bound the KL. So we have a term here, which is W2 between mu and E minus V. Here we have a square root of the Fisher information. Here we subtract C over 2. Then we have W2 mu E minus V. And this is for all mu. So maybe as a good exercise is just think about the case when C is positive, and also think about the case when C is equal to 0, and just stare at the inequalities for a little bit. So let me sketch how we can prove the theorems. It's probably because there was maybe a squared here and then the 2 comes down. It's something like that. Yeah. So let's start with theorem 3. And for theorem 3, we will use the fact that we actually know the Wasserstein gradient of W2. So we consider the map which sends mu to W2 squared between mu and E minus V. So this is also a functional on the Wasserstein space. And then it's a fact that if we look at the derivative of this map, it's just equal to minus 2 t of x minus x, where t is the optimal transport map between mu and E minus V. And again, if you want to convince yourself of this type of computation, just do the analogous computation for Euclidean space where you replace W2 by the Euclidean distance. So maybe, it just, if we have the gradient with respect to x of y minus x squared, then this is equal to minus 2 y minus x. So the y minus x is replaced by this term. Okay, so let's do this computation. So before we had a similar computation, and we used the bound by using the triangle inequality and all that. Now we will actually use an identity. So the identity just comes from the fact over there. So we just do the chain rule. Let's see, do I want this square? Yes, I want this square. And here mu t, yeah, I should have made it clear. We'll take mu t to be the gradient flow of H, not of the KL, but of H. So because mu t is the gradient flow of H, we know how to compute this derivative. So it's just equal to 2, and then we get Tx minus x because from the computation here. And then because this is the gradient flow of H, okay, so what we can do next is use the fact that H is convex. So remember here, the F, which was a KL, we were able, if you remember from last lecture, it was actually a sum of two terms. One was entropy, and then the other one had this integral of V. So because it was a sum of two terms, actually the derivative of the KL was the derivative, and the Hessian too was derivative of two terms, one from the entropy, one from the potential. This was a term corresponding to the entropy. This was a term corresponding to the potential. We don't have a potential now, so we only have this term here, which is always non-negative. So we have convexity, but we don't have strict convexity. To get strict convexity, we needed this potential as well, and then we needed to make some assumption that the Hessian of V is lower bounded by alpha. But alpha is positive. We don't have it here because we just work with the entropy, so we just have a non-negative term. But that's okay. So H is convex. We still can use it. So the convexity of H imply that if we look at H E minus V, which we should think of it as H mu infinity, minus H of mu t, is upper bounded by Tx minus x, and then the gradient of H at mu t. So remember, this is, again, this is a computation that Sinho showed, or rather stated, that the definition of convexity has a number of equivalent definitions, just like in Euclidean space. One of them was the tangent line definition, that the convex function has to be above its tangent line, and that's what's written here. Okay, so maybe to not belabor the point, I will just write again that you take a function phi t to be, this time you're going to take it to be 2t H mu t minus H E minus V plus W2 squared mu t E minus V. As usual, you show that phi prime is decreasing and so on. Okay, so I think I have 3 minutes. So let me just, again, do like a very quick sketch of the proof of theorem 4. Okay. So for theorem 4, we actually going to use a geodesic. So we're going to take nu of S, where S goes between 0 and 1, and it's going to be a geodesic between mu and our measure E minus V. And then what we do is we do Taylor, and we write, so I'll write like that. So this is KL of E minus V with respect to itself, which is of course also KL of nu 1 with respect to E minus V. And then we do Taylor expansion. So we expand around nu 0, and we will look at the second order term. So here we have the gradient of KL of nu 0 with respect to E minus V, and here we have the derivative of the geodesic at time equals 0. And here we have another term, so 1 minus S, and now we have the Hessian of KL. So now the question is how, basically we need to bound each one of these terms. So maybe not to hold people for too long. I'll just say, so the one fact that we need to use is that because nu is a geodesic, its norm is actually just equal, because it's a geodesic with speed 1, it's just W2, nu 0, nu 1, which are, of course, u and e minus v. How do you bound these two terms? In one of them, you just use Cauchy-Schwarz, and I told you we're going to use Cauchy-Schwarz once, so you use it on this inner product. And then for the second term, you use the lower, remember by assumption, we had a lower bound on the Hessian of v in terms of some constant, but remember that the Hessian of KL was related to this Hessian of v, so you plug that estimate and then you do some computations and you get it there. Okay, so the point of this lecture was just to show you how to use this type of calculus to derive functional inequalities, and by functional inequalities we mean things like log-Sobolev inequality, which related Fisher information, and relative entropy, and Talagrand, which related Wasserstein distance, relative entropy, or inequalities like that. The main application that we saw so far for functional inequalities of this type is to show how fast the gradient flow converges to its stationary distribution. And in the next lecture, we will show how these inequalities are actually related to probabilistic properties of the measure. So for example, the type of statement that we'll have is that if the measure satisfied log-Sobolev inequalities, then we can say something about how tightly it concentrates and things like that. That will be the topic of the next lecture. So I think I'll stop here and I'll answer any questions.